Hello everyone. In today's video, I am going to discuss about one more data structure by name Fibonacci heap. Before going through what do you mean by Fibonacci heap, I would suggest you to go through my previous video wherein I have discussed about one more data structure by name binomial heap. It will be easy for you to understand the different operation and the time complexity on performing on a Fibonacci heap. If you go through the operations in case of a binomial heap, because the operation are almost similar, and finally we'll just give a comparison between how different is the operation in case of a Fibonacci heap when compared to a binomial heap. Now coming to today's topic, in case of today's topic, initially I am going to discuss what do you mean by a Fibonacci heap and the properties of a Fibonacci heap, and then later on we will be discussing about what are the different operation and the time complexity in case of a Fibonacci heap. Now first we'll start with what do you mean by a Fibonacci heap. Coming to the definition of Fibonacci heap, note that the definition is related to binomial heap. Say that the first point in case of Fibonacci heap is, I have defined that Fibonacci heap is a heap data structure consisting of collection of data. Even in case of a binomial heap also, binomial heap was a collection of heap data structure. In the sense, it is a collection of min heap trees. Even a binomial heap was also a collection of min heap trees. The trees in a Fibonacci heap are not constrained to be binomial trees. In case of binomial heap, which was defined as a collection of binomial trees, there we have defined that a binomial heap, in a binomial heap, it was an ordered collection of binomial trees. But whereas here in case of Fibonacci heap, it is an unordered collection of binomial trees. You can find it in the fourth point. Unlike trees in a binomial heap, which are ordered trees, Fibonacci heap are unordered. Unordered in the sense, the root which were linked together in case of a binomial heap were a collection of ordered trees. I used to have B0, B1, B2, B3, B4 and so on. But whereas in case of a Fibonacci heap, it is also a collection of binomial trees. Not exactly that. One more important point in case of a Fibonacci heap is, in case of a binomial heap, all the binomial trees should have 2 power k nodes. But whereas in case of a Fibonacci heap, it is not necessary that each of the binomial tree, which is denoted with bk, should compulsory have 2 power k nodes. That is the third point. So, unlike binomial heap, Fibonacci heap can have many trees of same degree, and a tree does not necessarily have exactly 2 power k nodes. If you have noted, in case of a binomial heap, I can have only one B0, I can have only one B1, I can have only one B2 and so on. But whereas in case of a Fibonacci heap, I can have more than one B0, I can have more than one B1. And apart from that, it is not mandatory that each of the binomial tree bk, not exactly it should have a 2 power k nodes. And the other property of the min heap property even should be there even with respect to the Fibonacci heap also. That means to put together, leaving out this min heap property, let me denote. This might be a structure of a Fibonacci heap. I have 2 B nodes, but whereas in case of a binomial heap, we were not allowed. I am having 2 B1, and I am having a B2, but here I am not having 2 power k nodes. I am having one node less. In case of B2, I am supposed to have 4 nodes, but here it is having just 3 nodes. If you go through this property, it does not have exactly 2 power k nodes. And what is the other one? Unlike binomial heap, Fibonacci heap can have many trees with the same degree. So this was about the definition of a Fibonacci heap compared to a binomial heap. Now let's go for the properties of a Fibonacci heap and let's come up with a structure. This was a structure of a binomial This was a structure of a Fibonacci heap. Let's put some elements onto this and we'll see how exactly a Fibonacci heap looks like. Some of the properties of a binomial heap are, the first property is each node in a Some of the properties of a Fibonacci heap are, each node in case of a Fibonacci heap stores a degree. It stores a degree. That means each node in case of the Fibonacci heap stores a degree, which gives, this degree gives the number of children. In the sense, with respect to this example, I can say degree of 23 is 0, degree of 7 is 7 is 0, degree of 17 is 1, degree of 24 is 2, degree of 3 as 3. That means each node will store the degree of the node. Second one, in case of a Fibonacci heap, we use a pointer denoted with min of h, which points to the minimum node in the root list. We know that in case of a Fibonacci heap is a collection of min heap trees. Now, in case of a min heap trees, the root will store the minimum value, and this linked list which links all the root together. Now, there is a special pointer which points to the minimum of the root node, which, if you note, this was not there in case of a binomial heap. Now, with respect to this example, this 3 is the minimum among these 5 elements. So, a pointer by name min of h will be holding the address of node 3. Now, third point is each node in case of the Fibonacci heap x may also contain a mark of x. Mark of x is nothing but a Boolean field indicating whether x has lost a child or not. Say for example, now assume that this was my heap, and on this I am trying to perform a decrease key operation. Hope everyone knows what do you mean by decrease key operation. Assume that this was node x. The information stored in this x needs to be decreased further. Now while decreasing, if this has resulted, if this tree structure is being modified to something like this. This node is being shifted to root list, and this was parent node of x, and this parent has lost a child. So what we will do, we will mark this particular node. I'll call this particular node as y. So this y, if this is being marked, it implies that due to some operation, it has lost its child. So in case of a Fibonacci heap, each node in the Fibonacci heap can either be marked or unmarked. If it is marked, then it implies that that particular node has lost a child. So in this example, node 18, node 39 and node 26 are the marked nodes, which tells that due to some operation that their children were lost due to some operation. And note that newly created node will always be unmarked. In case of a Fibonacci heap, the newly created node will always be unmarked. So these are some of the important properties of a Fibonacci heap. And similar to that of the binomial heap, each node in case of this Fibonacci heap is a circular doubly linked list, has to be represented in the circular doubly linked list. In the sense, in the root list I need to create a circular doubly linked list. Node 7, right pointing to 3, left of 3 pointing to 7, 23 right pointing to 7, and 7 left pointing to 23. Now 3 right pointing to 17, 17 left pointing to 3. Similarly, 17 right pointing to 24, 24 left pointing to 17, and 23, I'll have one more pointer. 24 next, or 24 right are next pointing to first node left link pointing to last node. Now this applies even to the other levels also. Yeah, if you see, the node 3 has 3 children, so these 3 children will be connected together. Node 18 has only one child. (52) does not have any child. 38 has one child. Node 17 has one child. Node 24 has 2 children. And node 26 has one child. This is how a Fibonacci heap is represented. Let me call this as the structure of a Fibonacci heap. Now this was about what do you mean by a Fibonacci heap and what are the different properties of a Fibonacci heap. With this, we'll go on to some of the operation that we can perform in case of a Fibonacci heap, as well as we'll try to discuss the pseudo code as well as the time complexity of each of those operations. Let's come to the first operation that we can perform in case of a Fibonacci heap, the operation by name make heap. Now what is the objective? The objective of this make heap operation or the make heap function is to create an empty Fibonacci heap. So if you see, I have mentioned that it creates a new empty Fibonacci heap. What it will do, it creates, in the sense it allocates memory and it returns h. Now as it is an empty Fibonacci heap, the number of nodes in the heap will obviously be 0. So I'll be using a term by name n of h. So this n of h will be set to 0. This is nothing but the number of nodes in h. And as I told while discussing the property for a Fibonacci heap, we use a special pointer by name min of h, which points to the minimum element in the root list. Now, after creating a empty Fibonacci heap, this min of h should be initialized to nil. Now, coming to the time taken to perform this operation, it is just allocation of memory. Allocation of memory, and min of h is set to nil and n of h is set to 0. How much time it takes? It takes a constant time. So I can say the actual cost is a constant. Actual cost is a constant. Now coming to the amortized cost. That means in case of Fibonacci heap, for all the operation, we are going to discuss the amortized cost with the help of the potential function. So, the potential function that I am going to use in case of the Fibonacci heap is denoted with phi of h, which is nothing but t of h plus twice of m of h. Now what is this t of h? T of h is nothing but the number of trees in root list. Now in this example, how many trees are there in the root list? 1, 2, 3, 4, 5. Now what is m of h? M of h is nothing but number of marked nodes. If you remember, we have discussed about what do you mean by marked nodes. Marked nodes are those nodes which are last its parent. In this example, how many marked nodes are there? 1, 2 and 3. Now if I want to calculate phi of h here, phi of h for this particular Fibonacci heap, it is nothing but t of h is 5 plus 2 into 3. Which is 5 plus 6 as 11. Now, here in case of make heap, what is the amortized cost? The amortized cost is nothing but the actual cost plus the potential function, or the change in potential function. Now anyway, when I create an heap with no list, obviously this potential function pi of h, this value pi of h is 0. So what will be amortized cost? Amortized cost will be equal to actual cost. Actual cost is order of 1. It is order of 1 plus 0. This one. Hence, the time complexity or the amortized cost to perform the make heap operation in case of a Fibonacci heap is order of 1. Make heap takes order of 1 time. That is, it takes a constant time. Hope this is clear. This was about the make heap operation. Now let's go for the second operation by name insertion operation. Coming to the insertion operation, objective is given a Fibonacci heap denoted with H, I want to insert a new node onto this Fibonacci heap H. Do remember that in case of a Fibonacci heap, there is a special pointer by name min of H which points to the minimum element in the root list. Now in order to insert a new node onto this particular heap, what are the steps that we are supposed to perform? First thing is, for the node to be inserted, I need to create a new singleton tree. Say for example, onto this tree, I want to insert a new node with information as 21. With the key to be stored is 21. What it says? Create a new singleton tree. Now this is a new singleton tree. Now add to the root list. Now add this singleton node to the root list. Now what I will do? I will add this to the root list. Third step, update the min pointer if required. Now why I need to update the min pointer? Now, say for example, in this case, it was 21. That means x of key, this was my x dot key. X of key is 21, which is greater than compared to min of h. So there is no necessity for me to change the value of min of h. Assume that if this min of h is 3 and the new node to be inserted was 2. That means my x dot key was 2. Now what I am supposed to do? I have created a singleton node. Now add the singleton node to the root list. Now I need to add it to the root list. Once I add it to the root list, now the Fibonacci heap, I should make this min of h pointing to 2 because 2 is lesser than 3. I need to update this min of h to hold 2. So this is the step. Step is quite simple. Create a singleton node, add the singleton node to the existing Fibonacci heap. Now one advantage of this Fibonacci heap or binomial heap was, in case of a binomial heap, if there were two nodes or two trees of the same order, I need to merge them together. This is not required in case of the Fibonacci heap. Now add that singleton node to the root list of the heap. Now if the min heap if the key of the newly added node is less, then update the min pointer. Now coming to the time complexity. So how much time it takes? I need to create a new singleton tree. Now add it to the root list. And update the min. Now if you see, all these three takes only constant time. Creation, adding and update. Update in the sense you are just comparing only one comparison. 3 is compared with 2, you are updating. If 3 is lesser than the newly created node, then 3 remains as it is. So I can say the actual cost is a constant time, which is order of 1. Now coming to the amortized cost. So in case of the amortized cost, we have defined the potential function. That means what was the potential function? The potential function that we have defined is phi of h is equal to phi of h, P of h plus 2 times of m of h. No, this was the initial potential function. Now on adding a new node to the Fibonacci heap, what we have done? That means the potential function after insertion. Now what this has happened, what this has made is that pi of h is, if you note, this was the potential function before insertion. Before insertion was a t of h plus 2 times of m of h. Now after inserting, what it has done, we have added a new node to the root list. In the sense, t of h is increased by 1. So this becomes t of h plus 1. Plus, is there any change in the number of marked nodes? If you do remember, the property of the Fibonacci heap, newly created node will never be marked. So my marked node remains same. Now, so what will be the amortized cost? Amortized cost is actual cost plus change in potential. What is actual cost? This is order of 1 plus change in potential is phi of h dash. I will call this as h dash or something like that, is equal to this value. So this is t of h plus 1 plus 2 times of m of h minus change in potential is nothing but phi of h minus phi of h dash. If you do remember the amortized analysis chapter, change in potential was denoted with this. This is t of h plus 1 plus 2 times of m of h minus the whole thing. This is nothing but minus t of h minus 2 times of m of h. So this got cancelled, this got cancelled. So you are left out with order of 1 plus 1. What is the time? This is once again order of 1. If you do remember, that takes a constant. So note that insertion of a new node onto a Fibonacci heap takes a constant time. So this was about how to perform the insertion operation. Let's quickly go to the pseudo code of performing the insertion operation on the Fibonacci heap. This is the pseudo code for performing the insertion operation. If you see, the algorithm is being named as a fib heap insert, wherein there is a given Fibonacci heap for which I need to add x. So what are the steps? First, I am initializing x dot degree is equal to 0. If you have noted, while discussing the properties, I have told that each node will have a degree which tells you how many children it contains. So as it is a newly created node, it does not have any child, so it is 0, and the parent of that particular node is null. And then the number of children is set to nil, and x dot mark, that means I have told either the node in a Fibonacci heap, all the nodes in the Fibonacci heap can either be marked or unmarked. Marked in the sense it has lost the children. Newly created node will never be set to have a mark. So this x dot mark is set to false. Now if you are calling this insertion operation for the first time, then the Fibonacci tree does not exist at all. That means whatever x you have, you will create a node list. You will create a node list for h containing x. That means in the h, this will be the only node, and you will set min of h to this node. If a Fibonacci heap exists, say for example, if this is my Fibonacci heap and this was my min of h, don't worry about what is the information stored in each of this node. If this was my h and now I need to add this x to here, so what I will do, I'll just insert x here. It says that insert x into h root list. I have inserted x onto the root list. Now I will compare x dot key. If this is less than the key stored in this, I will make this, say for example, if this was 5, and this is 2 is less than 5. Now what I will do, I will update this min of h. Min of h will be this node. H of min is x. Now on adding this node x, The number of nodes in the Fibonacci heap is being increased by 1. Finally, I am updating h dot n. This is nothing but the number of nodes. H dot n is equal to h dot n plus 1. This was about the pseudo code of performing the insertion operation in case of a Fibonacci heap. Hope this is clear. This was about what do you mean by a Fibonacci heap, what are the properties of a Fibonacci heap when compared to a binomial heap, and how to perform the make heap operation and the insert operation. Note that in case of both the make heap operation as well as the insert operation, it takes a constant time. Both the actual cost as well as the amortized cost is order of 1. Hope this is clear. Thank you.